Welcome to the AMS 2940 online lectures. For the rest of the class, I'm going to do a number of these online lectures to try to demonstrate and show the final concepts that we need for this course. If at any times you have any questions, feel free to contact me and we will set up a time when we can talk online if you like, or we can just communicate over email. So the first of these concepts is dealing with assignment problems. Already we've talked about transportation problems being kind of a subset of your linear program where we had a different technique to solve them that was more efficient. Well, assignment problems are an even simpler form of these transportation problems where there is yet another technique that's even more efficient to solve them, something called the Hungarian method. So this model is a group of applicants applying for a group of jobs with known costs for each applicant job combination. That's kind of the classic formulation for this problem. The essential part is that you have a number of things that are being associated with a number of other things where only one item can be associated with one other item. So here's an example. A repair shop has 3 technicians available and 3 repair jobs to complete. There's an estimate of how much it would cost if each technician were sent out to do each job. So, for example, if you have the first technician doing the first job, it costs $4. First technician doing the second job costs $6. First technician doing the third job costs $8, and so on through the whole grid. The idea is that you want to assign a single person to a single repair job. If we put this in the context of what we've seen with transportation problems, this is really a transportation problem where the supply for every row is 1 and the demand for every column is 1. If you do that, you can solve this using the transportation problem methods that we saw earlier. But when you have that special case where all of the supplies are 1, all of the demands are 1, and it's balanced, there is another technique to solve them called the Hungarian method. This is the linear program for what we want to do. So you can see here that the main constraint or the main variable is a 1 or a 0. So it's either they get the job or they don't. It's binary. So in other words, it's integral and either 0 or 1. We're trying to minimize the cost, which you should be able to put together from our matrix. Subject to, well, these are the normal constraints where the first applicant, or the first technician in this case, is only assigned a single job, second a single job, and third is assigned a single job. These are for the jobs where it says that each job is assigned a single technician. Then finally, we have that they're all positive and they're integral. So here's the Hungarian algorithm. We start with the cost matrix, and we'll go through a couple of examples. Start with the cost matrix and find in every row, find the smallest entry. You subtract that from every row, every entry in that row. We call that the row reduced matrix. Then, with your row reduced matrix, look for the smallest number in each column and subtract that from everything in that column. That's your column reduced matrix. Now, here's the part that's a little bit tricky sometimes. With your column reduced matrix, draw the minimum number of vertical and horizontal lines that cover all the zeros of the resulting matrix. If you used n lines where it's an n by n matrix, then you have a solution. If not, then you subtract again from every uncovered entry the smallest uncovered entry, add to each covered entry on the intersections the smallest uncovered entry, and again draw the minimum lines. So there's a bit of an iterative process here, and you just continue doing that until you have the right number of lines covering all of your zeros. So here's a couple of examples. So first off, we did this one. I did this one out fully. So here's our technician. Our technicians being assigned to jobs. First thing, you look at all of the rows. So the first row, the smallest number is 4. Subtract it from every number in that row. You're left with 0 to 4. Look at your second row. 2 is your smallest number here. Subtract it from everything, and so on. Your third row, 5 is the smallest number. Subtract it from everything in that row. That is your row reduced tableau. Now start looking at all the columns. Smallest number in each column, well, it's a 0 in the first column, so that column doesn't change. In the second column, you have a 1, so you subtract 1 from every number in that column. Fourth column, you have a 0, so it doesn't change. That is your column reduced matrix, or column reduced tableau. Now, the second step is find the smallest number of horizontal and vertical lines that you can that cover all of the zeros. And that's what we do in this second step here. We found that if we cover there and there, we only need 2 lines to cover everything. And that's what we did here. Well, now the rule says that if you need less than n lines to do that, so in this case we only needed 2, but it's a 3 by 3 matrix, so that means that we're not done yet. So when we do that, we look at the smallest uncovered entry. That'd be the 1 right here. All of the uncovered entries, you replace them by 1 less. So that becomes a 0, that becomes a 3, that becomes a 1, that becomes a 2. And now you go to all of your intersections. We only have 1 number here that's an intersection on our 2 lines. And you replace that by whatever the number is, whatever your smallest number was. In this case, a 1. So it becomes, instead of becoming a 0, it becomes a 1. So what are you left with? You're left with the matrix down here. And when you cover it with the lines, you see you can't do it with 2 lines anymore. You need 3 lines to cover all the zeros. That means that you're done. You're done with your Hungarian method. So now the question is, what is your optimal solution? To find your optimal solution now, it's a matter of finding a 0. You find n zeros, 1 in every row and 1 in every column. So I'm looking for 3 zeros that take 1 out of every row and 1 out of every column. And you'll find often when you do the Hungarian method and you get down to this point, you do have multiple answers. It's not unusual that you have lots of ways of doing this. So for this, I need 1 0 out of every row and column. So first, if I look at my third column, I only have a single 0 here, so that has to be my 0. Now I look at my second column. Well, I can't choose that one, the middle one anymore, because I've already taken a 0 from that row, so it has to be this one. And then my final one has to be here. That is my solution. In this case, there is only a single solution. You will often get that there are multiple solutions. So this says you assign technician 1 to job 2, you assign technician 2 to job 3, and you assign technician 3 to job 1. So we have technician 1 with job 2, technician 2 gets job 3, and technician 3 gets job 1. And there's your solution. And this is just summarizing. To get the solution, you pick out a set of zeros, like I just described, with a single entry picked in every row and every column. That's exactly what I just went through. So, another couple of examples to finish this up. Dispatcher has 4 cars available to transport people. 4 people call up and request cars. And so you can look at the distances between the cars and the people to pick them up. So how should the cars be assigned to pick up each person? So let's go through the problem. We look at every row and subtract the smallest number from every row. In the first row it's a 4, so we subtract it from everybody. We get all zeros. The second row we have a 3, so we get 0, 2, 4, 5. Third row we have a 2, so it becomes 0, 2, 4, 6. And the third row we have a 3, 0, 1, 2, 3. That is our row reduced. Now we have to get the column reduced, which in this case is actually pretty easy because we've got a 0 in every column. So it actually doesn't change anything. So our column reduced is the exact same as our row reduced. Now, next step is to look at how can we cross out all the zeros. In this case, we only need 2 lines, but we have 4 columns, so we're not finished yet. Now, we look at what's left, what isn't crossed out. The smallest number we have is a 1, so we subtract 1 from all uncrossed numbers, and we add 1 at every intersection. So this becomes 1, 0, 0, 0, 0, 1, 1, 0, 0, 3, 3, 1, and 0, 4, 5, 2. And again, how many lines do we need? 1, 2, 3. We're still not there. Now we have the 1 again being the smallest number that is not crossed out. So we have to add that 1 to every intersection. This time we have 2 intersections. So this becomes 2, 0, 0, 1, 0, 0, 0, 0, 0, 2, 2, 0, and 0, 3, 4, 2. Now, how many lines do we need this time? Well, when you go through all of this, you find you actually need 4 lines to cross out all the zeros. That means we're done. So, what's the solution? We need 1 entry from every row and column. So here is an entry. That's the only one in that column, so it has to be there. Look at the next column. That one has to be your option. And now here's where you get your choices. You'll see that what's left in the rows and columns, you actually have 2 ways of doing it. So there's one way, and there is a second way of doing it. So taxi 1 is pick up 4. Taxi 2 is pick up 1. Taxi 3 is pick up 2. And taxi 4 has pick up 3. There's my solution. And that is the lowest cost way of doing it. So remember, the Hungarian algorithm can work for, these are transportation problems, but it's called an assignment problem because the supply and the demand is exactly equal to 1. Again, it has to be a balanced problem. So if you're not balanced, just like with our transportation problems, you can balance it by putting a virtual supply or virtual demand to balance it and then use the Hungarian method. Just remember, every row and column has to have a supply or demand of 1. That's the key point here. So as a final example, let's look at one where we do need to balance it. So here we have 3 applicants applying for 5 jobs and a certain cost for each applicant being assigned to each job. So we do need, we do need to add 2 rows to balance it out. But now we have a couple of other considerations. So normally if you just have to balance it out, you'd put in all zeros, the same way we did for assignment problems. But we do have the big M idea here as well. So we have a couple of things. One is that job 1 must be filled by some applicant. So in other words, it can't be left empty. A4 and A5 are these phantom applicants who they don't really exist. They represent jobs that are going to be left undone or unfilled. So what we're going to do is assign a big M to the cost of those, so they will never be left unfilled. It's also felt that applicant 3 should not be given job 5. So applicant 3, job 5 is no longer a 6. We're going to make it an M. The rest of them doesn't matter, so they are given zeros. And you'll note now when you do this that you do have an awful lot of zeros in there. So when you go to your row reduced and column reduced, you're probably not going to have too much to change. Now, that's just setting up your tableau. Then it's the exact same technique to figure it out. So, given your initial tableau, add in your rows, make the adjustments for things that you have to do or are not allowed to do, and solve it out. And I'll leave this one as an exercise for you to figure out. All right, thank you for your attention.